Welcome to today's session, Sustainability Powered by AI and Machine Learning. Hi, my name is Simon Johnston. I live in Sydney and have been part of the AWS team down under for over 3 years. I work as a principal AI ML specialist responsible for the machine learning business across Australia and New Zealand, and have the super exciting job of helping customers on a daily basis with their AI and machine learning journeys. This can span strategy or operations, but quite frequently solution capabilities and how to leverage their data to be more competitive, with one of the most common questions being asked is, how do I get started? For this session, we will consider this question of how to get started, but specifically rethinking sustainability powered by AI ML and how businesses can treat their data as an organizational asset for sustainability. Today, I am also joined by Eden, my colleague, who we'll meet later on. In 1987, the United Nations defined sustainability as meeting the needs of the present without compromising the ability of future generations to meet their own needs. This definition has been extended by others, Amazon included, and for today, let's consider through the lens of data and AI/ML what this actually means. So the question for this session is, what role would data science play in sustainability? Data is key, but how to access data? What data is required? And once you have the data, how should we go and solve the problem? In today's agenda, we have 3 sections. The first part of the session, I will discuss how leaders are adopting cloud technology to spearhead their sustainability objectives. In the second part, Eden will take a real-world example where Amazon.com has used machine learning to optimize their HVAC systems. Sounds simple, but this is actually a complex data science challenge that uses methods that can be extended to optimize the entire footprint of an organization. Lastly, we will wrap up and discuss how you can get started thinking about data and partnership. Since 2020, Amazon is the largest corporate buyer of renewable energy around the world, enough to power millions of homes a year. When it comes to operations, sustainability is a key driver. Why? Well, in order to meet its carbon emission targets and become net carbon neutral by 2040, Amazon must be efficient in its operations. Amazon is also a founding signatory of the Climate Pledge, a pact between currently 217 of the world's biggest organizations. Locally, there are companies such as FMG, Zero and Canva, pledging that they can work together to beat the targets set by the Paris Climate Agreement within 10 years. Sustainability is obviously wide-reaching and for leaders touches many areas of our economy and society, from how we decarbonise our business operations to water conservation and partner with others. There are all important elements of building sustainability in our organisations. Key questions are being asked in these focus areas such as, how do I reduce energy and water usage in my operations? This shifts the thinking from economy and society to technology solutions. And within technology, leaders are rethinking data as an organisational asset and understanding how it can be used to drive their sustainability objectives. Sustainability is complex. It's more than a single variable that needs to be optimised, such as fossil fuel use. But getting the right data is key. Organisations can struggle with complexity, so there is a responsibility on the data scientists to demystify this. When we think about Amazon's supply chain, Amazon had to rethink with data and machine learning to provide a global, scalable solution, removing traditional analytical processes which combined human-designed rules, decision trees, and localized statistics, with advanced machine learning techniques being holistically data-driven. This is no different for sustainability. Take the question of how do I reduce energy in my operations? There will be hundreds of thousands of different objectives or variables which need to be taken into account. Commonly, traditional best practices is to follow an analytical process, breaking the problem down into smaller pieces and solving for each piece separately. Teams are formed with specific KPIs to manage their piece. However, this does not necessarily lead to a global optimum. Teams optimize for their own KPIs. Some do better than others, and these might not translate directly to the overall organization objectives. Coming back to Amazon's operations, AWS technology is the machinery that powers their operations, and we bring a few examples of the pioneers adopting AWS technology to also achieve this. Lots of other AWS customers are also rethinking about how they leverage their data. And when we think about agriculture, the global population is experiencing major growth, with the United Nations projecting an increase from 7.8 billion today to 9.8 billion by 2050. To meet this growth, agriculture must produce more food with less water. In fact, farmers already use 70% of available fresh water and 50% of habitable land today. CropX is an agriculture startup that is addressing this need with a focus on soil data. Most agricultural companies rely on above-ground data, such as satellite imagery, meaning a small number, potentially less than 10%, get data from within the soil. The advantage of soil data is it allows speed of insights, for by the time there are visible signs of crop stress detected from space, the damage is already done. CropX are using AWS to harness raw data, process it in real time, and provide recommendations that are specific to the crops, the geography, and the soil, so farmers can be predictive and preventative to determine whether a plant has received enough fertilizer even before the plant knows. Jumping industries to transportation, did you know every year truckers in the United States cover more than 95 billion highway miles? Enough actually to travel the globe over 3.7 million times, with billions of dollars being spent on trucking. However, this is not necessarily an efficient industry. A staggering 40% of the miles truck drivers log each year are done with an empty truck, representing a costly waste of time and fuel. A large part of the problem is the industry's infrastructure, an aging, fragmented network of shippers and haulers, big and small, joined together by brokers that match one side with the other. This process often relies on traditional methods like email, address books, and phone calls. Using Amazon SageMaker, Convoy's machine learning models analyze millions of shipping jobs along with trucker availability, then recommend matches that are cost efficient and timely. This impacts everything from routing and prices quoted to shippers and truckers to recognizing what types of loads match best with individual drivers. A mobile app is built on top of the SageMaker solution and is used to connect drivers and shippers, reducing millions of miles driven in the US every year by empty trucks. Data undoubtedly plays a big part in addressing sustainability challenges. Once the data has been made available, there is still the challenge of managing the complexity of the analysis. This can be tackled using the AWS services to accelerate your sustainability journey powered by AI/ML. And for today's session, we suggest 3 enablers to consider. Number 1, at AWS, we often say the right tool for the right job. AWS provides a number of AI machine learning services. For example, I mentioned SageMaker being used by Convoy. This is a service that was actually born out of Amazon to remove the undifferentiated heavy lifting of machine learning and allow data scientists to do what they do best: build, train, tune, and deploy models into production. So think about your teams, their capability, and their personas, and matching up the right tools. Secondly, combining the tools with other storage, database, and visualization capabilities provides a platform to make this easier. So whether you're looking to centralize and standardize, building a scalable and secure environment to evolve and future-proof, democratizing access to teams. And thirdly, thinking big and starting small is important. So selecting a use case that is A, achievable, and B, will demonstrate downstream impact is important. During the next session, Eden will actually bring this to life. The last example I wanted to leave you with today is a company called Carrier Global. They are a leading provider of sustainable building and cold chain solutions. Carrier understood the importance of their data and a need for a platform. Co-developing with AWS, Carrier has brought to the market their new Lynx digital platform, which ingests various data sources and has been built using AWS IoT, analytics, and machine learning services, along with Carrier's refrigeration and monitoring solutions. This offers a suite of tools to carrier customers around the world, providing, for example, enhanced visibility, increased connectivity, and actionable intelligence across their cold chain operations to improve outcomes for temperature-sensitive cargo, including food, medicine, and vaccines. So effectively it allows the business to extend their current digital offerings for managing the temperature-controlled transport and storage of perishables. New benefits such as end-to-end tracking, real-time alerts, automated processes, and predictive analytics to help them deliver temperature-controlled cargo more efficiently, in turn decreasing the cost of cold chain operations by optimizing resource utilization, cargo loss, and spoilage, and thus helping to prevent waste. Looking ahead, Carrier and AWS plan to introduce a new capability for the Lynx platform to provide recommendations related to cargo and routing and improving fleet utilization. This adds greater resilience into the cold chain that will help Carrier's customers to manage costs, schedules, and resources. So really thinking big and extending upon their first project. The platform and tools are built on AWS allows this. Now I will hand over to Eden.
Hi, I am Eden and I work as a Principal Data Science Manager at AWS. My team helps companies around the world to achieve their sustainability objectives. Today we are going to go through an example from Amazon.com, which came to AWS to help them optimize their energy use for cooling their buildings. This is a strategic area which asset-intensive industries are focusing on. On average, cooling accounts for 40% of total building energy consumption. The problem that we tackled was to optimize the operations of economizer rooftop units. These units mix in outdoor air into the building with the aim of reducing the energy use in heating and cooling and releasing air from the building via a return stream. They usually operate using set points for outdoor and return air temperatures and pressures. They will turn off, for example, when the outdoor air reaches a specific set point, for example, 24 degrees. The opportunity for optimization lies in the fact that if the outdoor air is cooler than the inside, it isn't always the case that less energy is required for cooling. Hence, deciding when to turn on the economizer plays an important role in saving energy. AWS took a two-step process to solve this problem. We first used machine learning, supervised learning in particular, to build a simulator which could predict the energy use. We used a range of features gathered at the current time to predict the energy use at the next time step. With this model in hand, we were then able to simulate how the system behaved in response to changes in what we wanted to control, in this case, turning the economizer on or off. Then we use this simulator to determine the optimal policy for engaging the economizer given the conditions. We used a method called reinforcement learning for this. Reinforcement refers to the use of a reward at each step to condition the behavior. If the reward is positive, the agent learns that it's doing the right thing. If it's negative, it takes that feedback on and corrects its behavior. We trained an agent to learn an optimal policy in order to maximize the long-term reward. So in this case, the reward was the negative of the total power consumption for cooling the building for the individual economizer unit. We also maximize the entropy of the policy using the SAC method. What this does is it allows the policy to explore and not to assign a very high probability to a narrow range of actions. This stops it from getting into a local minimum and settling on a range of actions that might not be positive. So let's take a look at the underlying infrastructure which was used to put this solution into place. To start with, we saw how the historical data was used to predict the power use. This included data like temperature, pressure, humidity, and airflow. To build up the dataset, AWS Lake Formation was used to set up a secure data lake to manage all the historical data. This improved the stability of the core data lake and reduced manual operation and maintenance costs. Then Amazon EMR was used to manage and manipulate the data using Spark. Finally, Amazon SageMaker was used as the main platform to train the prediction models, accessing the data through Amazon EMR. An AWS serverless architecture has been prepared for a pilot to manage model inference in production. To start with, Amazon Kinesis is used to stream in real-time data from sensors to be used for inference, which is then stored in Amazon DynamoDB to be used by the models in AWS Lambda to provide the recommendations. The control system will then be able to connect to AWS over VPN by calling an AWS step function to receive recommendations for the economizer set points. So now let's take a look at that solution in action. You'll see here is a schematic of a rooftop unit economizer. It takes in the outdoor air in the bottom left-hand side of the picture, through past a sensor, which measures the temperature and humidity of that air, through a cooling unit, and into the building on the bottom right, also past another sensor measuring the cooled air. Then once the air's coming out of the building in the top right, it then can either return to the outside or be recirculated back through into the building. The first thing that we're going to do is we're going to extract the data from the data lake. So in this case, what we use is a schema called bricks. So bricks is a standard schema for building data that we've converted our data into, and then it makes it very easy to find and extract that data from the data lake. In this case, what we use is a Spark SQL query, and we can very easily write that query using common English terms to identify the sensors that we want. In this case, we're looking for that outdoor and return temperatures and humidities. So you can see here that we've written a Spark SQL query that then runs in the database and runs against this bricks standard and is able to pull back the data without having to go and search for all these different tags that you might not understand and could be buried in. There could be thousands and thousands of sensors in a particular building, and it can be very hard to find exactly what you're looking for. So that's the advantage of converting it to bricks. It makes it very easy to get started. So we'll run that query now. So now we've retrieved that data frame. We've got the data. And what we're going to want to do is we build that supervised learning model that predicts the energy use of the building from this data. So we first build that model, and then we can use that model as a simulator for optimization. So in this case, we've tried 3 different optimization methods. The first is the ASHRAE standard, which is just simply using a static set point. That's an industry standard method. The second method we use is a black box optimizer that we're going to need to train on the data because we're going to need to run that on that historical simulator. And what we're using there is Bayesian optimization to find the optimal set point for a static set point. And we use a Bayesian optimization method very similar to what you might use often for hyperparameter tuning for your supervised learning models. And the final method that we use is a reinforcement learning agent, which is we use that SAC method to find an optimal policy on the simulator. So we're going to go ahead and train that black box simulator and the RL agent on the simulation of data. The training is running, and we first get that black box set point method. And we're running the RL agent over 1,000 time steps that in practice, you would run this over a lot more. It could take some hours to train. But in this case, you get relatively reasonable results just in 1,000 time steps, and it runs relatively quickly. So we're running that agent. And you'll see here that we've got that black box agent has set a particular set point for the process. So we've set a temperature and enthalpy that can be used as an optimal set point. So now we've got that, we're going to go and evaluate these different methods on the simulator itself. Now, when you're doing this in practice, you would always hold out a separate test set and build a simulator based on that test set. and do the evaluation that way. But in our case, for the sake of a demo, we found that the results were very similar whether you held out a test set or not. So we'll just use this same simulator for evaluation. So what we're going to do is run those 3 different methods, the 2 set point methods and the RL agent, over that simulator. So we load in the reinforcement learning model there, and we will run that simulator. So it's running those 3 different methods, and it runs it over many, many different trajectories of the simulator, and then averages the results over those. So we see here the results. So this chart shows you the total power consumption of the unit and shows the 3 different methods. So you can see that the black box simulator actually does fairly well. It reduces when you see the power consumption by roughly a bit under 2%, which is quite impressive considering you're just creating a set point there. And you can see also that the RL agent does significantly better. That's because it can change more over time is the main thing. But we'll see that in the results section. The result in simulation was a 2% reduction in power use compared to the industry standard step point method. Have a look at this chart. It shows what you have just seen in the demo, except the y-axis is the negative of the power consumption. This is because we used it as a reward for the model, and we want to maximize reward. So higher is better. You can see that after an initial learning period, a reinforcement learning agent, which is the light blue line at the top, is consistently better than the other techniques. You can see how it changes dynamically over time, going up and down. This is what allows it to outperform the other methods, which prescribe a static set point over time. The RL agent disables the economizer whenever the outside air requires more power to cool compared to the recirculated air in order to be able to reach the desired indoor air temperature. So 2% may sound small, but applied across the large network of buildings at Amazon, it will reduce costs by millions. This example was chosen as it is relatively simple, but illustrates the methods and how effective they can be. In the same way, these methods can be applied across most industrial operations and have been effective at reducing total power consumption by about 10% for AWS customers. On top of this, global optimization can be applied to achieve even more efficiency. For example, in an office building, it's possible to coordinate the economizer with the chillers and external shading, minimizing the total energy consumption. So this illustrates the important role AI/ML has in achieving sustainability objectives, helping to manage the complexity which Simon mentioned before. So get started now, and you may be surprised at what can be achieved. The question is, can you afford not to? I'll pass back to Simon now, who will give you some tips on how to get started.
Thanks, Eden. Such a super real-life example. What data you needed, tools you leveraged, and approach you adopted. When we think about large sustainability initiatives, they can be difficult to accomplish alone because they often require a broad range of skill sets. That's why leaders are working with organizations experienced in cloud technology, sustainability, and machine learning innovations to speed up their digital transformation and create a lasting improvement. We advise customers to consider machine learning as a journey, working backwards from the production. The technology is enterprise ready. The question is how to apply and get started. Through the AWS ecosystem, there are many ways we support customers, from solution architects to professional services to our very own machine learning solutions lab. And we have a massive partner ecosystem, which are all here to help. We have lots of resources, so feel free to reach out. Now, machine learning needs data, so I'd like to introduce you to 2 initiatives. The first is the Amazon Sustainability Data Initiative. It's a program to reduce the cost, time, and technical barriers to extracting knowledge and insights from large data sets. Using AWS and its scalable infrastructure and associated computational services to address this problem is advancing innovation in this space. Through the program, we provide cloud grants to democratize access to the data and compute for innovators and researchers in all geographies. For example, to use their data for climate change mitigation strategies and actions. On the other side, it helps data providers by improving awareness and dissemination of their data, which encourages use of their data by making it easier to access and co-locating it with compute resources. This decreases the need of IT infrastructure on their side. It also helps users because they no longer have to take on the cost of discovering data, accessing it, acquiring it, storing it, and cleaning it, an Achilles heel for any data science project. The second initiative I want to discuss was the AWS Data Exchange, which makes it easier for AWS customers to find, subscribe to, and use third-party data in the cloud for their environmental, social, and governance, i.e. ESG analysis and projects. Actually, in just a few minutes, customers can find more than 3,500 data products in the AWS marketplace from over 200 qualified data providers. There is a strong selection of data across financial services, healthcare, life sciences, location-based data, and aggregated consumer data. So data sets can be used for climate research, to screen portfolios of unsustainable assets, inform insurance pricing, reporting on environmental, social and governance disclosures, and inform areas for diversity, equity and inclusion improvements. Numerous subscriptions are free of charge, while others may carry a fee. Datasets can come from organisations such as the SASB, an independent, non-profit organisation that sets the standards to guide disclosure and connect businesses and investors on financial impacts of sustainability, covering different frameworks and disclosure topics. Another example dataset is from Verisk Maplecroft, a global risk and strategic consultancy firm from the United Kingdom, which provides insight into country, sector, corporate and supplier level exposure, basically the full spectrum of political, economic, human rights and environmental issues. Additional AI and ML resources can be found at the AI Hub. This contains some excellent ebooks on use cases and infrastructure considerations. Also, visit the links to start your ML training and certification journey. So thank you very much for attending today. From myself and my colleague Eden, we wish you much success in your sustainability journey. Go build great AI. We also really value your feedback to help us improve our sessions. So please complete the survey. Thanks.